We gave them enough time. Let's get started. So, my idea for today, quickly review our basic rules here. Now, first off, let's keep in mind, we've been talking about two types of rules. We've been talking about rules of logic, and then these rules. What are our rules of logic? Those are things that we demonstrate are tautological implications. These are our rules of derivation, or our rules of deductive reasoning. So two separate things. One of our rules here tells us we can use rules of logic. So let's quickly recap what each of these rules are. Our rules of derivation. So first we had rule P. P for premise. This was a rule that we may introduce a premise at any point in our derivation. Nothing wrong with that, because in our derivation we keep track of what conclusions fall from what premises. So if we introduce a premise, we keep track of all the conclusions that fall from that premise. So that's perfectly fine. Rule T, here's our main rule that we use. This is a rule that says we may introduce some proposition, some statement, some proposition S into our derivation, provided S is tautologically implied by previous lines of our derivation. So that's, by tautologically implies, we mean there's some rule of logic that says this follows from previous lines of our derivation. That's what that rule enables us to do. So that's our rule that enables us to use laws of logic, or rules of logic. Rule CP for conditional premise. This is a rule that enables us to remove a premise. This is what we do in our algebra classes all the time. Your teacher says, show that if x equals 2, then 2x equals 4, something like that. You introduce x as a conditional premise. You show that implies this. And when it's all said and done, what you showed is that x equals 2 implies 2x equals 4. We do not always and forever say x equals 2, and we do not always and forever say 2x equals 4. So we introduce a premise conditionally, show that implies a conclusion, and then we back out and we say, okay, so we show this implication follows from the rules of arithmetic. And this is not a new premise of arithmetic. So what does it say? It says, if we can derive S from R and, what's fancy P?
All the prepositions.
All our premises. It's the conjunction of all our premises that we introduce using this rule. So if we can derive if we can derive S from R and fancy P, in other words, if R and fancy P together imply S, then we may derive R implies S from our premises alone. The truth table we wrote out to help give intuition for this was showing that P and R implies S is logically equivalent to P implies R implies S. If knowing P and R tells you S, then knowing P tells you if you know R, then you know S. Those say the same thing. And so we introduce R like this as though it's a premise, and then we get rid of it and we say what we've concluded is that R implies S. And then finally, the last rule that we introduced, our rule RAA. Remember what the RAA was? Latin phrase?
Reductio ad absurdum.
Yeah, reductio ad absurdum. We showed that it can, whatever you said can be reduced to an absurdity, is where that comes from. So how does this one work? If a contradiction is the most absurd thing you can utter. You utter a contradiction. That's something that's for sure false. Can't be true. It's absurd. If a contradiction can be derived from your premises and not having S, then we may derive then S may be derived from our premises alone. The truth table we did for that is P and not S. If P and not S implies false, so that's not F for a statement, that's false as in false on a truth table. Something that's for sure false, a contradiction. So if P and not S imply F, that's logically equivalent to P implies S. In other words, we showed it's impossible for S to be false, therefore, if your premises are true, S must be true. Your premises being true and S being false is impossible, therefore, if your premises are true, S must be true. Intuition. Okay, so that's quickly recapping those rules. Now, what I want to do, first off, remind you guys that there is no timetable for this class. We can take as much time with all this stuff as you guys want, making sure we get our foundations well established. So, what I thought might be a good idea is I'm just going to start running through homework problems up to the point that we're at. So I'll just start going through exercises, solving them, and then if we feel like some are becoming tedious and we get the point we're not getting anything from it, just tell me and we'll move forward to the next batch and move forward to the next batch. and quickly get to where we are in the book. That make sense? Anyone think that that's a dumb idea for any reason? Anyone just being polite?
No.
I already did the homework, but
You already did the homework?
yeah.
Cool. Well, you can pull it out and check it if you want.
I used ChatGPT to tell me if I got it wrong.
Dangerous.
You're getting pretty good.
That's cool. Okay. So first batch of exercises. This is going back to talking about truth functional sentential connectives. That's what's trying to help us grasp. So a classic example of a non-truth functional sentential connective is that of possibility. As a general rule, we use, this comes from modal logic, but we use the triangle to represent possibly. Something is possibly the case. Now this is not truth functional. How do we know that possibly is not a truth functional sentential connective? Let's set up the truth table for it really quick. And let's set up a couple propositions to analyze with it. So first off, we'll let alpha be a statement. The statement the author chose to use is there's life on Mars, because that was something that it's not really known. We could pretty much say there's no life on Mars now, but Europa is a moon of Saturn, and there's speculation that there's life on Europa. So we'll make this life on Europa will be our alpha here. Now, alpha is either true or false, right? Either there is or there isn't. But right now, is it possible that there's life on Europa?
Yes.
Is it possible that alpha is true? Yes. Is it possible, regardless of what the truth or falsity of it is? Right now, it's possible that there's life on Europa. On the other hand, let's now make beta the statement 2 plus 2 equals 5. So here's our beta. Beta, again, well, we know that beta is always false. So in this case, beta is always false. But is it possible that we have beta?
No.
No. In each case, it's false. So in one case, I plug a false statement into possibility and I get true. In another case, I plug a false statement into the possible operator and I get false. So possibly is not truth functional. It is not simply a function of the truth or falsity of the sentence you give it. It instead depends upon the actual content of the statement that you give it. And so it is not truth functional.
Wouldn't it be just true in all cases unless they were all false? Kind of like what would the correct term be?
Well, we could pick some other example. You will complete, say you were given some task at work. You will complete that task tomorrow. It's possible that you will, and it's possible that you won't. Right?
Right, because there's scenarios where it could be false, and scenarios where it could be true.
Yeah, so looking at that statement, so this time we make alpha the statement, partly we'll complete that task tomorrow. That is true or false.
Oh.
But right now it's possibly true, and right now it's possibly, the fact that you will, it being true is possible, and it being false is possible.
Oh.
On the other hand, if we made the statement, partly will prove 2 plus 2 equals 5 tomorrow, no chance.
Right, because it's always false.
Because it's always false.
So it's a if you were to
Yes, possibly, intuitively, it means it's not guaranteed to be false. That's what possibly means. Following our intuition. Yeah. Okay, so there's one example of a non-truth functional sentential connective. Another one is Mr. Smith believes. Mr. Smith believes that. Give you some statement alpha, the sky's blue. Or we'll pretend he's a flat earth guy. And we make alpha the statement, the earth is round. Is it true that Mr. Smith believes that the earth is round? In that case, no. But maybe he does believe it. We have no idea, based off the truth or falsity of what we feed that sentence, whether or not the resulting statement is true or false. We would have to know Mr. Smith. And it would be dependent upon Mr. Smith, and it would be dependent upon whatever the statement is that we fed in. And it's not just a function of the truth or falsity of what we feed in.
Isn't that what we call a predicate?
No. A predicate is something like x is greater than 3. It's something that we can't determine the truth or falsity of it until we replace our variable with some term, some constant. X is greater than 3 is a predicate.
Yes.
You can't call it true and you can't call it false. But once I replace X with a number, it is true or it is false.
Isn't that kind of similar to how you're saying, well, it depends on what...
We are not anywhere into predicates yet. Right now we are just looking at statements. This is a sentential connective and we add some statement in there. And is the result simply a function of the statement we gave it?
But it just, sounds like what you're saying is we're just, we can't determine the truth or falsity of it because there's some variable that hasn't been quite defined yet.
Well, it's somehow dependent upon the content.
Yeah.
And so it's not just a function of the truth or falsity. Truth functional means it's simply a function of the truth or falsity.
Yeah.
Alpha and beta, if you tell me the truth and falsity of alpha and you tell me the truth and falsity of beta, I can always evaluate that expression, and there's nothing else to it.
With the word deterministic.
Regardless of the content.
Regardless of what alpha was talking about and regardless of what beta was talking about. I just need to know whether that's true or false and whether that's true or false, and now I can evaluate the whole expression.
Right.
Just because I give you something true here doesn't mean you can evaluate the truth or falsity of that. That's what we mean by truth functional.
Okay.
And then finally, it is necessary that. Necessary is a counterpart to possibly. Necessary means it couldn't have been otherwise. So let's say Parley finishes his task tomorrow. Is it necessary that Parley finishes his task tomorrow? No. So we fed it a true statement, but it spits out false. Now, on the other hand, it is necessary that 2 plus 2 equals 4. Yes. So I feed it a true statement in one instant, it spits out false. I feed it a true statement in another instant, and it spits out true. So it is not simply a function of the truth or falsity of the proposition we feed in there. It depends upon more than that. So it's not a truth functional sentential connective. Good? Alright. Let's see. Which of the truth functional connectives introduced in this chapter would give us unless? So let's think about what unless means, and let's think about what it logically means. So alpha unless beta. What exactly does that mean?
Alpha is true unless beta is true.
So to give this to me in terms of sentential connectives, we already know. In terms of not, and, or, implies, equivalent. What exactly is the logical structure of unless here?
Alpha or not beta?
Alpha is true or not beta?
My first guess.
Alpha unless beta.
You'll fail this class unless you do your homework. What does that mean?
It's a condition on it.
There's a condition on it. You'll fail this class unless you do your homework. If you do your homework, what do you know?
You didn't fail the class.
Not necessarily.
Is that what it means?
I don't.
B implies that A.
If you didn't do your homework, what do you know?
Wait.
You'll fail the class unless you do your homework. Let's say you didn't do your homework.
Fail the class.
So we have not beta implies alpha.
Right.
Is another way to say it.
So it's beta or alpha. No, that can be right. Never mind.
Another way we could say it is saying you'll fail the class unless you do your homework. It's also saying the same thing as you won't pass implies, not alpha, meaning you pass, implies you did your homework. So another way to think about it is not alpha implies beta. Notice that's just a counterpart to that, or the contrapositive of that.
Okay.
You'll fail the class unless you do your homework means if you don't do your homework, you fail the class, or it means if you pass the class, you did your homework. Now actually, the way you thought about it here is perfectly fine. It also means you failed the class, or, wait, is that right?
No.
No. You would have to put,
No, if you failed the class or, oh wait, you did your homework.
so it would be that, if we want to or together.
Yeah.
Alpha unless beta.
No, because can they both
You
be
failed the
true?
class, or you did your homework. You'll fail the class unless you do your homework. You failed the class, or you did your homework.
So it's just or.
But is it inclusive like or is?
Yes, because we know that alpha implies beta. Let's scratch it to the side here. Maybe to not get confused with letters, I'll use different letters. A implies B is the same thing as not A or B. which is how I thought about it. So I'm just applying that to this, or applying that to this one.
But since you're
Not
applying-
your antecedent or your conclusion.
If you apply not on your alpha, you basically get it.
Well, I'm just saying this says the same thing as that.
It does. Okay.
So that's all was my thinking. Applying that rule from this to this is the way I was thinking about it. So here's a bunch of different ways that we could encode the unless word.
But it seems like alpha unless beta implies that if beta is true, alpha is false.
That's right there.
But that's not how OR works.
Alpha, beta, alpha, unless beta. So, true, 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 false, false, true, false, false. And maybe just put a quick alpha or beta here to compare it to. And this one we instantly know is true, 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 false, right? No point in that. Okay, alpha unless beta. Let's get some markers. I don't know how good that's going to work with English. We'll make alpha is I'm holding the red, beta is I'm holding the purple. I'm holding that doesn't work very good, does it? So let me write down what our encoding of the sentences were, and then we'll just think about it in each case. So we made alpha equal to you will fail. Don't know why I capitalized that. And we'll make beta equal to you do your homework. Okay, so let's say that both you fail and you do your homework. Ooh.
Right.
How do you, yeah.
Right, it doesn't work. It implies that if beta is true, alpha is false.
Let's say you fail and you do your homework. So, no, that still works. Because when I say you will fail unless you do your homework, that doesn't mean that
Just because you did your homework.
just because you did your homework, you don't fail.
Right.
Yeah.
It just means that if you don't do your homework, you for sure fail.
Yeah.
So that actually works.
That's why I said necessary.
So this is true. If they're both true, alpha unless beta is still true. Right?
It would have to be.
So now let's try the next one. Let's make alpha true and beta false. So you fail your class and you did not do your homework. Is it true that you failed the class unless you did your homework?
Yes, you did not.
You failed the class and you didn't do your homework.
Yes.
Yes, that's true. Let's look at the next one. You failed the class is false, so you passed the class, and you did your homework. Is it true that you'll fail the class unless you do your homework?
Mm-hmm.
Yes, in that case, still true. And then finally, let's say they're both false. Let's say you passed the class and you didn't do your homework.
False.
Is it true that you'll pass the class unless you do your homework? No, that's the only case where it's false.
So we're just literally using the word unless, and we could replace it with or, and it would mean the exact same thing logically.
Yeah, so unless logically means the same thing as or, the same way that but logically meant the same thing as and. Okay, so that was a neat little one. Alright, translate the following compound sentences into symbolic notation using letters to stand for atomic sentences, and then plugging in our truth functional sentential connectives. So, let's go through these. Either the fire was produced by arson, or it was produced by spontaneous combustion. So if we were to symbolize that, that would just be arson or spontaneous combustion. And that's how we'd symbolize that. Next one, if the water is clear, so this is an implication, we're saying if water is clear, then what? Then Henry can see the bottom of the pool, or he's a nincompoop. So Henry or nincompoop. Where should my parentheses be?
H or N.
Should or those two, it should be around those two. We're saying if this is the case, then we have that or that. Perfect. Next one. Either John is not here, or Mary is, and Helen certainly is. So tell me what to write first.
J or
J for John is here, or
or M,
M, Mary is.
and then I'd probably quote wrap.
Put parentheses around those.
Yep, and then and Helen Strange.
Perfect. That's exactly right. Last one. If there are more cats than dogs, so we'll use C for more cats than dogs, and it's an if, so we're implying something, then there are more horses than dogs, we'll use H for that, and there are fewer snakes. And then the implication, parentheses go like that. We're saying if this is the case, then we have both those.
So with C, where we say John is not here. No, I mean, probably, yeah. John is not here or Mary is.
Oh, we forgot
Yeah.
not.
Yeah, what do we do about the not? Yeah, that.
Not John is here or Mary is.
Okay.
Yeah, there you go.
Yep. Good. Anything else we missed?
I often, I just assume that the comma is generally what determines where the parentheses go.
It is.
Okay.
So let's jump into a bigger one. If either housing is scarce or people like to live with their in-laws, so we'll do H for housing is scarce or live with in-laws, we'll do L. If we have one of those two, then and so let's see. If either housing is scarce or people like to live with their in-laws, and if people do not like to live with their in-laws, and not L, okay,
Yeah.
all that, boop, 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 implies
Housing is scarce.
housing is scarce. So if we know H or L, and we know not L, then we for sure know H.
And that is,
Okay. I think we're good with writing those out. So let's evaluate some expressions. So we're right here. So we're evaluating, I think, the truth or falsity of each of these. So let's symbolize each of these. So we'll use G for the Galileo one, D for the Descartes, N for the Newton, R for the Rason. Don't know who that was. And in each case, we know that G is a true statement. Descartes was born in the 16th century. That is true. Newton was born before Shakespeare is false. And then finally, Rason was a compatriot of Galileo is false. So now let's symbolize these and then evaluate them. So if Galileo was born before Descartes, so that's G implies, then Newton was not born before Shakespeare, so not N, right? That's symbolizing it. Now we're supposed to evaluate this expression. When it's all said and done, each of these should evaluate to true or false, just like some algebraic expression. So G is true, not N is true. True implies true is true. So this whole thing right here evaluates to true. Next one. If either R, Rason was a compatriot of Galileo, or Newton was born before Shakespeare, so if we have that or that, then Descartes was born in the 16th century. That's what we're evaluating. So let's see. False or false is false. False implies anything is true. Next one. If Rason is not a compatriot of Galileo, so that's the negation of that one, right? Not R, then Descartes was not born in the 16th century. Let's see, this said was born, so
Yeah.
not D or N. And then parentheses like that, right? So let's see. R is false, so not false is true, implies, let's see, not D, so false or false is false. True implies false is false. So this whole thing evaluates to false. Good? Looks like example 5 is very similar. Which of those are true, which ones are false, by evaluating them. I don't know, you want to do more of those, or you think you're good? All right, we'll try a big one. So we'll jump to this one. Looking at I here, or that's a J. Looking at J here, so P, did he give us the truth and falsity of them? He gave it to us in an annoying way. P, Q, and R are true. So P, Q, and R are true, S is false. And now let's evaluate this. So true implies true is true, which implies that's that arrow. We'll put a bracket here. True implies true is true. Implies true implies false is false. Okay, and then true implies false is false, and true implies false is false. So this whole thing evaluates to false. Okay. So I think we're good on those. I think it was mostly just confusion about truth functional sentential connectives. That was probably causing confusion. Let P be a sentence such that for any sentence Q, P or Q is true. Okay, so I know P or Q is true no matter what P is. What can we say? P is a sentence such that for any sentence Q, the sentence P or Q is true. What do we know about the sentence P?
That's true.
P must be true. Because P or anything is always true. True or Q, we know, is always true. The only way for that to be the case is if P is a true sentence. The other one's probably similar. Let P be a sentence such that for any sentence Q, the sentence P and Q is false. Okay, so for any sentence Q, P and Q is false means P must be false. Because false and anything is false. All right. P is logically equivalent to Q. What can be said about P or not Q? So I know either they're both true or they're both false. They're logically equivalent. What can I conclude about this? True or not true is?
Oh,
So let's look at the case where they're both true. True or not true evaluates to true. And false or not false evaluates to
True.
true.
Yeah.
So it's a tautology. So this implies this would be a tautology. If we know this, we for sure know that.
sure.
Okay, let P, Q, and R be any three distinct atomic sentences. Decide by truth tables which of the following sentences are tautologies. Oh boy. That's just P and Q. Let's just pick one. Which one of those looks the best?
The worst. Yeah, just do.
The worst, so I better extend this line, is what you're saying?
Yes.
L's pretty
So we got P, Q. We can have true, 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 false, false, true, false, false. All right, read me the first chunk we want to look at.
Bracket. Oh, are we looking at the?
L.
We want to look at the whole thing.
Unless we're doing a smaller one.
Which one are you picking?
L.
We're picking L? Okay, so let's try and get some bite-sized pieces of this thing.
One thing I like.
Geez Louise. Okay, I'll do this, I'll do that, I'll do that. Do we want to do that?
One thing I did is I just replaced all the P's and Q's with their actual. Wait. Can't remember what I did. But once I did it, I basically solved it like algebra.
Yeah, let's kind of think about this algebraically for a second. Q implies Q is always true. So this piece is always true. And with true is like multiplying with 1. Doesn't change anything. So this whole thing has the same truth or falsity as just this piece right here. And whatever this evaluates to, the whole thing evaluates to. Right? Q or not Q is always true. Well, that piece is always true. P and not P is always
False.
false. False implies anything is always
True.
True. So now we're looking at P and Q implies something that for sure is true. When is an implication that implies true actually true? Always. So that was a tautology. Okay, easier to just kind of simplify it than it is to write out the truth table. But we could have done the truth table and it would have been more tedious and more brainless. But would have for sure worked. Okay, any of those other ones look interesting you want to analyze?
I think there was one that used
J.
R, O is K. K
Okay.
uses R.
Okay. All right, let's look at you. So P and Q implies P is logically equivalent to Q or R is true. So trying to think, is there a way that we can make, when is an implication false? When the antecedent is true and the conclusion is false. So if our premise here is going to be true, P and Q have to be true. Right? And so this right here, keep track of where our parentheses go here. That's how our parentheses would go. So the only row on the table we really need to think about is when P is true and Q is true. Because when P is false and Q is false, it's trivial. So we only care about when both of those are true. And now we're looking at, and we want to handle when R is true or when it's false. And then I'll use A for that big ugly expression. And let's analyze it in each case. So let's look at when R is true. True or true is true. True, logically equivalent to true, yes. So if R is true, then it comes out true. Let's look at when R is false. False or true is true. True is logically equivalent to true, yes. And so it is in fact a tautology. So both those were tautologies.
I'm not entirely sure how exactly P and Q is given that they would be true.
Okay, let's look at if P is false. P and Q is,
False.
false implies anything is, so
Okay,
it's true.
You can ignore all those.
Yeah, so ignore all the cases where your antecedent is false,
Got it. Okay.
because it's obviously true. So we only need to worry about the case where the antecedent's actually true. Good? All right, so seeing that those are tautologies, let's see this one. If P and Q are distinct atomic sentences, which of the following are tautologies? Is that a tautology? P being logically equivalent to Q? Obviously not, so no. Let's look at this one. P is the same thing as P or not? P or P? If P is true, true is the same as true. If P is false, false is the same as false.
This or P or.
Yeah, is P logically equivalent to P or
Oh,
P?
Yeah.
Yeah. So this one, check. All right, P or Q, logically equivalent to Q or P?
Yes.
Yeah, it doesn't matter what order we're in. P implies Q, the same thing as Q implies P? Absolutely not. Those are very different things. If there's fire, there's oxygen. It's not the same thing as if there's oxygen, there's fire, or we'd be in a lot of trouble. And then P is logically equivalent to P. Is logically equivalent to P? Yes. So, check? No.
Wait, hold on. No, that's not true. I don't really think that's true for a second.
Just plug in true or plug in false.
Okay, if P is logically equivalent to P, which is always a true statement, doesn't mean that the over there, the P on that side is true or false. It could be false and the other side could be true, therefore they're not logically
Just
equivalent.
evaluate it. Plug in true for P. Is true logically equivalent to true?
Yes.
True. And is true logically equivalent to true?
Yes.
Yes. Plug in false.
What if it's false?
Oh, good catch. I was waiting for thinking that. Yeah, that's interesting. Good eye. Okay.
Lucky.
That's not lucky. You stopped, you thought about it, you didn't just listen to me. That's good. Okay. Next one. On the basis of ordinary usage, construct truth tables for the sentential connectives used in the following example. Okay, not both P and Q. What does that mean? sometimes called NAND operator. So PQ, and then here's P NAND Q. That's what they're getting at. True, 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 false, false, true, false, false. And tell me what's right here. So, we're doing not both P and Q,
False.
false. Not both P and Q,
True.
true. Not both P and Q,
True.
and not both P and Q,
True.
true. So it's a negation of AND.
Um,
AND is true, false, false, false. NAND is false, true, true, true.
oh, it's not.
This is your basic circuit that you use when you build up your logic circuits. You start with the NAND one, and you can build everything else from NAND.
I was thinking XOR. And it's
You
not.
can build XOR from NAND.
Okay, I thought that's what we were talking about.
Well, I don't know if there's another one, but in my circuitry course, that's the one we started with. So we built a NAND gate, and then we built everything else using NAND gates over and over again,
Right.
and built a whole ALU.
That was fun.
It was a ton of fun. Okay. Neither P nor Q.
I'm actually a little stuck here. Not both P and Q. I guess if it says not P and Q.
Right, they're getting at not P and Q.
Right, but when they say not both P and Q, they mean more than that.
No, this is exactly what they mean by not both.
Okay, well then that would be not P or not Q.
This is the same thing as not P or not Q.
Okay. And are you saying NAND is the same thing as not P or not Q?
Yes. We're saying P's false or Q's false. P's false or Q's false. P's false or
Okay,
Q's
yeah.
false. P's false
It's
or
the
Q's
reverse
false.
of or. Got it. Or, yeah. It is.
Whatever's cooking. Alright. So the next one is, this one, I don't know a name for it. Neither P nor Q. It's just a neither P or Q, which is the same thing as not P and not Q. And so that one, I don't know a symbol for it, so P, Q, there it is. It's when that is false and that is false is the only time it's true. Outside of that, it's just false, right? Cool. Give examples of sentences P and Q such that the following compound sentences are tautologies. Okay, so our job now is to come up with a P and Q that converts these things into tautologies. Right now, P and Q is for sure not a tautology. What could I replace P with and replace Q with such that the result is now a tautology?
Things that are always true.
Things that are always true. So give me something I can replace P with.
Like a sentence.
Yeah, but you could just give it to me in terms of
Can't
that symbols.
True. I don't.
Well, no. We need to be a tautology, meaning no matter what interpretation you make. So we can't just do 2 plus 2 is 4. You're picking a sentence that is true. But our result isn't going to be a tautology because say you want to replace that with the sentence 2 plus 2 is 4. We'll call that alpha. And we want to replace this with 4 plus 4 is 8. Call that beta. This is still not a tautology because it's not true under every interpretation. I now get to interpret your result, and you've got to make so that no matter how I interpret your result, I'm forced to call the result true. So that does not work. So we're going to replace it with some combination of symbols that are always true here, and that are always true here.
So 2 tautologies.
Yeah,
Like P implies P.
like P implies P. Okay, we can replace the first one with P implies P and
Q or not Q.
Q or not Q. That works. Now we didn't have to stick with symbols P and Q. We could have did alpha implies alpha and beta or not beta. So P implies P is always true. If you know P, you know P. Yep. And then Q or not Q. Yep, that works. And you can essentially apply the same trick to, I think, all of them. But maybe there's more clever ways we can think about. Let's keep going with them. So let's look at this one. What can I replace P with and Q with such that this becomes a tautology?
Well, let's see what's wrong with it first.
It's just not in general true. Plug in false for everything. False for everything gives you something that's false. Make those false, make that true. Still gives you something that's false.
So Q would have to always be false. No.
Does
Yeah.
it-
Well, we just need P to be something that's always true, and we're done.
Oh, that's true. I could be or not be.
Okay, so we'll replace P, just so we don't get confused, with alpha or not alpha. Now since we're interpreting it, whatever I replace this P with, I have to replace that P with.
Yeah.
That's one of our rules. So or, and then we have, I'm going to replace that parenthesis now with a square bracket, replacing P with alpha or not alpha, and then finally and not Q.
Right.
We can just replace Q with Q and we're fine. So true, this is always true, or anything is always true. True or anything is true. True or true is true, true or false is true. So we don't need to evaluate the rest.
But the and there, oh, gotcha.
Okay. Let's try this one out. P implies, just remind you of your precedents in case you don't remember. Parentheses go there. So, what can we replace it with?
We should make P false.
Make P false. So what should we make P?
Let me think. What's the logical contradiction?
A contradiction. Alpha and not alpha.
Yeah, that one.
There you go. So alpha and not alpha implies, square bracket, alpha and not alpha, and not Q. So now, the antecedent is always false, so the whole thing's always true. Because contradiction's always false.
Are there as many, whatever you call the opposite of a tautology, are there as many of those as there are tautologies, or are there very few? Things that are always false, I mean.
Things that are always false. I don't know. Had this conversation a little bit last time. My gut is that if something is always false, it is somehow always encoding an actual contradiction. And this is somehow hidden in there. Now there's going to be an infinite number because I could always just add onto this and beta. And there's another contradiction, but it had that in it.
But that's pretty much the basic form of something that's always false.
Yes, alpha and not alpha. I think that will always somehow be encoded in it somehow, if you get something that's always false. I could very well be wrong.
Whereas there's a ton of basic forms of things that are always true that don't look like that.
Yeah.
I think so. I could very easily be wrong.
Well, yeah, well, no, we know there's a ton of things that are always true that don't look like that.
Right, but maybe there's secretly some way that they could be reduced in some common structure to them. I don't know. I highly, highly doubt it, but I haven't spent enough time playing with it to have any confidence about it. Okay, finally, P implies not P.
Just make P false contradiction.
Be false.
Yeah, just make P a contradiction, replace that with contradiction. Contradiction implies anything.
Implies not a contradiction, which would be always true.
Yeah, false implies true is true.
Contradiction implies.
A contradiction is always true. If you give me one contradiction, I can come up with all the contradictions you want. Okay, so those were interesting. Is there any sentence P such that P and not P is a tautology?
No.
Remember, we can add substructure. So I can replace P with something that has substructure and replace that P with the same thing. Is there a way I can replace it such that this ever is a tautology?
You can't take away the not, right?
Nope, can't take away the not, can't take away the and. And so you're correct. There's no way to do it. This will always be false, no matter how you interpret the P. Nothing you can do about it. Because however you interpret it, it's ultimately going to be something that's true or false, and that's ultimately going to be the opposite of it. Doesn't matter what substructure you add. Okay, if P and Q are distinct atomic sentences, the sentence P and Q tautologically implies which of the following? Alright? In other words, if I know P and Q, what else do I know? Do I know P? Yes. Do I know Q? Yes. Do I know P or Q? Yes. Since I know them both, I know one or the other has to be true. I know both of them are true. Do I know P and not Q? If I know P and Q, do I know P and not Q?
Oh, yes.
Okay, wait a second.
No, you don't.
Are we assuming P and Q is true?
Well, what if P and Q is false? False implies anything is true, and so we don't need to handle that case. It's just like in our derivations.
Yeah.
I say if x equals 2, then 2x equals 4. You say, well, if x doesn't equal 2. Well, who cares?
Okay.
But we're still implying that P is true and Q is true if it's be a tautology, otherwise it would not be, correct?
So in order for P and Q to tautologically imply something, that means that every time this is true, the consequent has to also be true.
Also, we're just doing P and Q implies
Implies P.
simple.
Yes. So the first one was P and Q implies P.
Okay.
Is that a tautology? Yes. P and Q implies Q. Is that a tautology? Yes. P and Q implies P or Q? Yes.
Because P and Q.
If I know P and Q are true, do I know P or Q is true?
Oh, no, I thought we were talking about P.
Oh, sorry, now D. If I know P and Q is true, do I know P is true and Q is false? Absolutely not.
But is P is true and false? False. Okay. Right.
Next. If I know P and Q, do I know P is false or Q is true?
Well, that's true. Yes.
Yes. If I know P and Q, do I know if Q is false, then P is true?
Yes.
Yes. Let's evaluate this one for a second. So we're looking at the expression P and Q implies not Q implies P. Here's what we're evaluating. We're saying, is this always true? Now notice that obviously the whole implication is true when the antecedent here is true. Or when this is false. Because false implies anything is true. Right?
Oh, yeah, so they have to be true for it. That is the only scenario.
So
that is
if
false.
P is false, then P and Q is for sure false. False in anything is false. And so the whole thing is true. If Q is false, then false in anything is false. False implies anything is true. So the whole thing's true. So it's obviously true when P is false or when Q is false. So the only case we need to check is when P is true and Q is true. So let's evaluate that one. So if P is true and Q is true, P and Q is true. True implies, let's look over here. False implies true is true. And then true implies true is true. So yes, this is tautologically implied by this. Make sense? Finally, if I know P and Q, do I know P is logically equivalent to Q? Yes, because I know they're both true. Alright, that was interesting. If P and Q are distinct atomic sentences, not P or Q, tautologically implies which of the following? Okay, kind of the same thing. Let's finally jump to this one. If P and Q are distinct atomic sentences, the sentence P is tautologically equivalent to which of the following? Kind of the same thing, but I guess we'll do one more. So if I know P, do I know P or Q?
Yes.
Yes. If I know P, do I know P or not P?
Yes.
Yes, I always know P or not P regardless. If I know P, do I know P and P?
Yes.
If I know P, do I know P implies P?
Yes.
If I know P, do I know not P implies P?
Yes.
Yes, because false implies anything is true. If I know P, do I know P implies not P? No. If P is true, I do not know that if P is true, P is false. And then finally, parentheses go right here. Do I know that if P is true, then Q or not Q implies P?
Yes.
Let's think about that one for a second. Here's what we're evaluating. We're saying P, that's this P, implies this whole thing, I'll put in brackets. That whole thing we have Q or not Q implies P. Now if P is false, false implies anything is true, we're done. So we just care about the case where P is true. So we're looking at true implies. Now Q or not Q is always true. So true implies true. True implies true is true. True implies true is true. So it works. Okay. That's enough of those. Whew. Took more time than I thought it would. Some exercises here. Construct specific counterexamples for the following two fallacious rules of inference. The traditional names of the two fallacies are indicated. Who cares? Okay, so here's a common fallacy. If I know Q and I know P implies Q, do I know P? if I know Q is true, and I know P implies Q is true, am I able to include P?
Yes.
No.
Hold on.
Let's come up with a concrete example for P and Q. I'm going to do P is,
Yeah. It's oxygen, fire.
Yeah. so P is, there's oxygen. And I'll make Q is, there's fire. Okay, so let's see. Is it true? Oh, I need a Q that's already true.
It's if Q is true, are we implying that P is true? And this is a common fallacy.
So, swaparoo, P, Q. Okay. So, I'm making Q true and P implies Q true. Is it true that if there's fire, then there's oxygen?
Yes.
Yes. Is it true that there's oxygen? So is Q true? Is Q true?
Yes.
Yes, there's oxygen. Is it true that if there's fire, there's oxygen?
Yes.
Is there fire?
Not necessarily.
No. Well, I'm saying right now here in this space.
No.
So we're coming up with the counterexample. So that's our counterexample from that. Here's the second one. If I know P's false, and I know P implies Q, do I know Q's false?
No, we don't know.
No.
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 I mean, big hint, it's called the fallacy of denying the antecedent. So, for sure it's not true, but make it quick with your intuition, and I think this counterexample will work once again. Is it currently true that there's no fire?
Yes.
Is it true that if there's fire, then there's oxygen? Oh, so there must be no oxygen. No. So, bad logic. Very common one. This is the most common, they're actually the same thing. I guess I gave them different names, but one's just looking at the contrapositive of the other. And this is the one that I see used the most by people of those. Read a book by a PhD girl, and she did that left and right. Drove me nuts. Went from alpha implies beta to not alpha implies not beta all over the place. Okay, using criterion 1, decide which of the following are valid rules of inference. Okay, so just saying whether or not they're a valid rule of inference. If I know P and Q, can I derive P and Q? Yes. If I know P and P or Q, do I know Q?
Yes. Well, if it's true, you would. Because if P is true, then the Q is determined.
You know I'm a teacher, and you know I'm a teacher or I'm a billionaire. Do you know I'm a billionaire?
Q would be true. Wait.
No, I just gave you one where these were both true, and that's for sure
Right,
false.
Yeah.
You think too highly of me.
Why was A even an example? From P and Q, we may derive P and Q. What is that?
Making sure you understand that symbol? I don't know. I didn't write it. No idea. Or maybe he's thinking if P's on a line and Q's on another line of our derivation, then you can put P and Q on the same line on some other point on your derivation. Maybe he's trying to make sure you understand that.
And he's saying if P is true and Q is true, is P and Q true?
Yes.
Is that what he's saying?
Yes. That's exactly what he's saying. Okay. If I know not Q and I know P or Q, do I know P? Is that a valid rule?
I would say no again. But I don't know.
You just say P and Q?
So I know P's false. I know P or Q is true. Do I know P's true?
Yes.
Yes.
Oh, so it doesn't.
I know one of them's true. Q's false. Therefore P has to be true.
Oh, okay. That now clicks for me.
And then this one, if I know P or Q is true, and I know P's false, do I know Q's false?
No.
No. So that's an invalid rule. I in fact know Q's true. I know the exact opposite of what they're saying. Good? Suppose someone proposed as the only rule of inference, from P we may derive Q or not Q. So let's assume that we have this as our only rule of inference. Parentheses are like that. Which is a valid rule of inference. You can derive Q or not Q from anything you want, including from P. It's always the case that you have Q or not Q. So that is a valid rule of inference.
Is
Suppose someone proposed it as the only rule. Does this violate criterion 1? What was criterion 1? Criterion 1 is our rule of logic. These criteria were for deciding whether or not we accept something as a rule of logic. So our rules of logic, criterion 1 says that they have to enable us to only come to true conclusions. Could I ever come from a false conclusion using this rule?
No.
No, so it's good for criterion 1. Does it violate criterion 2 on the other hand? And the answer is yes, because we can hardly conclude anything from that. If that was our only rule of logic. If I was doing a derivation and this was the only rule I could use, I would hardly be able to derive anything.
What's criterion 2?
Oh, sorry. Assume you guys just know these as well as I do. Criterion 2 is a criterion that we have to be able to derive anything that logically follows.
This is all out for sure. For
Every conclusion that follows from our premises. So we want our rules of logic to enable us to conclude only those things that follow from our premises and everything that follows from our premises.
I read this over and over and over and over and over and over, and I still didn't understand it. When it says when we can derive only from like the premises that follow, I'm like, why can you just add Q? I get that it's a tautology, and that maybe they're magically you can apply them any way you want, but it was just bothersome that they say you can only come from the premises that follow, and then we're gonna add Q and not Q just for fun. Like,
Q or not Q.
Like, yeah, that you can add any tautology you want. It's just the description and the.
Yeah, so I could be going along a derivation, and I can know something like P. Now I could be trying to do some analysis of Q. I can introduce as a line out of nowhere, okay, I know Q or not Q. I know it has to be one of those, and continue on my merry way.
Yeah, but and that makes sense, and I don't, based off the way he words it, I don't understand how that's allowed, even though I can see why that should be allowed.
The reason it's allowed is because the sky's blue or the sky's not blue follows. From what? From whatever you want.
So that's basically saying that I should be able to include any tautologies that I want to.
Basically, yeah. That's exactly what it means.
Doesn't matter what I
Include them in
add
what?
into the
In his derivation. You can insert them in your derivation. You can always insert a tautology into your derivation. Yes. Because a tautology is always true.
Yeah, I just couldn't see how you could do that based off of the criteria. But I can see intuitively why that would be the case.
Alright. Construct a non-valid rule of inference, which by itself satisfies criterion 2, but violates criterion 1. So come up with a rule of logic that would enable us to prove anything that is true, but would also enable us to prove some things that are in fact false.
False implies true.
False implies true. So we can do something like alpha, well,
Not alpha implies alpha.
we know false implies true. So what would our rule of logic be? I mean, here's a simple one that we could add. P implies Q. There's one. You can derive Q from any statement P. If we introduce that as a rule of logic, now we can derive anything we want.
Right. So you
Or if you're worried about that one, we could do P or not P, and then put it like that. Because we can introduce that as a line, since it's a tautology, and then that implies that, and be on our merry way. But I think he was looking for something just like alpha implies beta. If we made that a rule, we could do whatever we wanted.
I swear, maybe 2 hours on this. I still don't understand it.
If you went and watched his lecture from last time, he went over vacuously true and it made way more sense.
Is that what we're?
Yeah, that's why that is the case. If false implies something, you can just prove whatever you want.
I did watch this video.
I guess you could think about that. If we introduce a contradiction as something that we can just insert, then yes. So if we also enabled us to have as our rule of logic, alpha and not alpha, if we inserted that as a rule, then now, applying an implication to that, P is always true. So there's another way you could do it. Okay. Next one. Utilize the discussion of sentential interpretation. Explain exactly why the following. We won't worry about that anymore. Which applying sentences are sentential interpretations of the sentence, it is raining or snowing? Okay, let's do that one. So which of these are sentential interpretations of this? Now, in order for it to be a sentential interpretation, it has to maintain the overall structure of this. We can add substructure. We cannot remove the existing main structure. So, if it's raining, then it's snowing. Is this an interpretation of this?
No.
It's a super sneaky interpretation of
because
this.
you can.
Because this is the same thing as not raining. So over here, this is the same thing as not raining or snowing.
So basically,
That's what it is raining. If it is raining, then it is snowing. It's sneakily this. Remember, alpha implies beta is the same thing as not alpha or beta.
But
So
I
an
thought-
implication is encoding a disjunction. It just negates that thing.
but I thought you couldn't throw in the not or remove the not.
We're adding substructure. We're still applying the not before the or. It's just our final structure, our highest level structure, has to stay or for this to stay in interpretation. So it is raining or it is snowing. A valid interpretation of that is it is not raining or it is snowing. That's a valid interpretation. We only added substructure. Does that make sense? Okay, let's try another one. It is snowing. Is this an interpretation of this? No, because it completely got rid of this disjunction. This one still had the disjunction in a sneaky way. This one, the disjunction's gone. It's not there anymore. Okay, it is snowing or it is snowing. Is this an interpretation of this?
Remove the raining.
We replace this with a sentence, and we replace this with a sentence, and the or is still there. It's a valid interpretation.
Okay, so.
But you replaced them with the same values. So you took a P or Q and you made it a Q or Q.
That's perfectly fine as an interpretation.
I guess that makes sense.
You can't do the inverse. I can't go from P or P and interpret that as P or Q.
Okay.
In our interpretation, we have to replace the same sentence with the same sentence. But a perfectly valid interpretation of P or Q is P or P.
It would be like adding something that's logically equivalent as a substructure to P. Is kind of what we're doing.
I'm not sure what that means.
Meaning, if something's logically equivalent to P, which you could then just label as P, and it would work, right?
Well, we're just replacing an interpretation. Is you can replace any atomic sentence with any sentence you want,
Including.
as long as you do it in all occurrences. Now, this only has one occurrence of each sentence, so we don't need to worry about that.
I see.
But we replace this with one and only one sentence. There it is. We replace this with one and only one sentence. We happen to choose the same sentence for both those. We don't care.
Yeah.
Still an interpretation. And in fact, this is an atomic interpretation because we replace each sentence with another atomic sentence. This one was not an atomic interpretation because we added some more substructure. We added a sentential connective. So, not only is this an interpretation, but it's an atomic interpretation. Next one. It is snowing or it is raining.
Yes.
Yes, we replace that sentence with that sentence. We replace that sentence with that sentence. Valid interpretation. Finally, either it is snowing and it is raining, or it is not raining.
Yes.
Yeah, let's write out the structure of this. This one is just an alpha or a beta. Down here, let's write the structure of this. Well, we'll write it out using R and S to R or S. That's what this one is saying. Now this next one, what's it saying? Either it is snowing and it is raining. So we get snowing and raining.
Replaces R.
Or not raining.
Yeah.
So we replace a sentence with this whole sentence, and replace that sentence with this whole sentence. And our or is still there. To add our parentheses again, we apply the not before we or it. And so this is the highest level operation. It's the last one we evaluate. That's what I mean by we added substructure, but we kept the existing structure. That will always happen in an interpretation. Not necessarily add substructure, but you could have added substructure. You can't get rid of existing structure. Good?
I still don't understand A. If it is raining, then it is snowing.
Okay, so this right here says R or S. This one down here says,
R implies S. No, it doesn't
not
say
R.
It doesn't say not R.
you're right. It says R implies S.
Right.
R implies S is logically equivalent to not R or S. To say this is logically equivalent to saying that.
I see.
It's so counterintuitive, but yeah.
Makes sense.
So that was a sneaky one. The rest of them are more straightforward. Okay. Let's see if we got some more of these interpretation ones. Which of the following assertions are true if false? Give a counterexample. Not as interested in that. Oh, maybe it will tell us about sentential interpretation. So let's go through it anyways. So a sentential interpretation of a sentence P must always have the same number of distinct atomic sentences as P. And the answer there is false. Because I could take P or Q. I could take P or Q. And a valid interpretation of that is A and B or C and D. I replace that with this sentence. I replace that with this sentence. This one has 4 distinct atomic sentences, whereas our initial one only had 2 atomic sentences. So this is saying does your initial one and your final one have to have the same number of atomic sentences? A sentential interpretation of a sentence P must have the same number of distinct atomic sentences as P. No, the interpretation can have more. It can also have less. Oh, that would probably be another one. Shouldn't have told you that. A sentential interpretation of a non-atomic sentence P must have the same major sentential connectives as P.
Yes.
And that one is true. In other words, if this one has an or, then the interpretation better have an or. So read that one more time. A sentential interpretation of a non-atomic sentence P. Why is he saying a non-atomic sentence P? He's saying a sentence that has structure. So what we're interpreting has to have structure. Because otherwise there's no structure to be preserved. So a sentential interpretation of a non-atomic sentence P must have the same major sentential connectives as P. Our interpretation must have the same major sentential connectives? Yes. Can't lose structure. A sentential interpretation of a sentence P must have the same number of occurrences of a sentential connective as P. And that one is false. Here's another interpretation. This is an interpretation of that. How many times does or show up here? Just once. How many times does or show up here? 3 times. So this one says, a sentential interpretation, this, of a sentence P must have the same number of occurrences of sentential connectives, like ors, ands, nots. The answer is no. Finally, a sentential interpretation of a sentence P must have at least as many occurrences of, not necessarily distinct, atomic sentences as P. So the interpretation has to have at least as many, not necessarily distinct, atomic sentences as this.
Yes.
Yes, it can have the same number of atomic sentences or more if we add substructure. It's impossible for it to have less. But wait a second. Couldn't I do something like this? Replace P and Q with just A or A? Isn't this an interpretation of that?
Mm-hmm.
And doesn't this have only 1 atomic sentence?
I guess.
No, it has 2 atomic
Occurrences.
sentences. Right, occurrences. Not necessarily distinct.
Yeah.
So that's why he put that parenthesis in there. So he's saying we're still counting 2 in this instant. And if you're still counting 2 in that instance, then it's either the same or you added more. You can't do less. Alright.
We're learning about logic, but we have to understand logic to understand what he's writing about logic. So,
It's always the second time through that you get it. Okay, so now we're getting to the sections introducing all our rules. We did that. Here's where he gave us our rules of tautologies. Did I skip example 5? No, we haven't done reductile absorb yet, right? This is still just that. Okay, so these exercises now are going to be exercises doing derivations. Let's just pick one. I don't know, you guys care which one we do? So let's do this one. If the market is perfectly free, so we'll use F for the free. So here's what our first premise is going to be. Write down our premises as I read them out there. So if the market is perfectly free, then, so if there's a default, it's a free, then single suppliers cannot affect prices. So then, single suppliers cannot affect prices. There's our first one. Okay, next one. If single suppliers cannot affect prices, S, then there are a large number of suppliers, N, 3. Moreover, there are a large number of suppliers. Therefore, the market is perfectly free. So we're trying to prove F from this. So put that up here. This one, we introduce using rule P, introduce premise at any point. It's only dependent upon 1 for its validity. This one, rule P, only dependent upon 2 for its validity. This one, rule 3, it's a premise. Premise 3, and it's only dependent upon 3 for its validity. Rule P, not rule 3. Okay, so now we're trying to conclude F from all of this. Right? So we know S implies N, we know F implies S.
So S must be true. Oh, wait, that's a common.
So we're trying to prove F is true.
So we know N is true, therefore S has to be true because N and S implies N. And if N is true, then S is true.
If I know S implies N, and I know N, do I know S?
Yes. If there's fire, then there's oxygen. Oh, wait. Wait, no.
No, because N could be false.
Yeah, this does not, these,
No, N
this
has
is
to be
not
true.
enough information to conclude F. So
No, I
there's
didn't-
something weird going on.
It says N.
Let me read the instructions.
No, this is correct.
It's an impossible proof.
No, it isn't.
It is. So
Okay, think about
for the
okay.
following arguments in exercise 2 through 14, try to construct sentential derivations like those in examples 1 through 3. If some case the argument is logically invalid, in such a case, right, conclusion does not follow, and they give a sentential interpretation which will show its invalidity. So I need to come up with an interpretation where this is true, this is true, this is true, and yet this is false. Okay? So here's my interpretation. F is going to be 2 plus 2 equals 5. S is going to be interpreted as 2 plus 2 equals 4. And N is going to be interpreted as 1 plus 1 equals 2. With me? So N is true. S is true. True implies true is true. False implies true is
True.
true. So this is true, this is true, this is true, and yet F is false. So the conclusion doesn't follow. Okay, so that's why I had no clue what to do.
Yeah, you're right.
So let's that wasn't very interesting. Let's do a different one. Problem 3. Okay, if prices are high, then wages are high. So P implies W. That's our first premise. Prices are high, or there are price controls. So prices are high, or there are controls. Also, if there are price controls, then there is not inflation. Controls imply not inflation. However, there is inflation. And then therefore, wages are high. So we're trying to prove W. Okay. Let's see if W follows from this. Okay, yes it does.
We know that C is true.
So this is one that we can for sure do. Okay. So what do you want to see first?
Well, okay, so this is where I made my mistake. Where if C implies not I, is true, then C cannot be true.
So C has to be false. Perfect. If C was true, I is false. But I is true. If C was true, I is false.
Yeah.
But I is true. So C must be false. So not C is tautologically implied by lines 3 and 4. And this is now dependent on premises 3 and 4 for its validity. Right? Another way to see that, look at the contrapositive of this. The contrapositive of this is I implies not C. So we know I implies not C, therefore we know not C. Another way to see it. That's the way I personally look at it, but whatever floats your boat, so to speak. Okay.
Or a better way. If C
We know
is-
not C, so now what?
If C is definitely false, and P or C is true, P has to be true for that statement.
Perfect. P or C is true, but C is false. So P must be true. If I know you got the soup or the salad, I know you didn't get the salad, you for sure got the soup. So, soup is tautologically implied by 2 and 5. And this is now dependent upon 2, 3, and 4, right? For its validity.
Yeah.
Okay, so now we got P. So P, and P implies W. So 7, we're able to conclude
P definitely, then W definitely is true.
W. This is tautologically implied by 1 and 6. And now we are dependent upon premises 1, 2, 3, and 4 for our validity. So yes, if these 4 lines are true, then that is for sure true.
I already did these, so I probably am cheating.
It's fine. Okay. I don't know. Was there one you found particularly interesting? You
It
remember?
just got progressively more challenging.
Okay, then let's jump to one. If they got progressively more challenging, let's just jump to the end one.
What I just want to do is not give the answer. I want you guys to have to go through the thought process.
Well, that's fine. I doubt you memorize the answer, and you just have to rethink through it every single time.
That's true.
So, let's, I won't worry too much about that. Just say whatever occurs to you. Alright, so we'll trust that they get progressively harder and jump to the end one and see if we get stuck. So, if Brown did not enter into the contract, or if Brown performed the contract, Brown did not enter into the contract is what they're going to use C for, and perform the contract is what they'll use P for. Okay, so those are distinct. So, entered into the contract, if Brown did not enter, so not contract or, what was the other one?
P.
Perform, P, then that implies what?
Smith will not win the lawsuit, which is W.
Not W.
Not W
That's correct.
or W? Not W?
Not W.
We're going to get tight here.
Yeah.
Let me push my P's over.
I like your the syntax format.
Yeah, I don't like the way the author does it.
Yeah, this is way better
And
because it's almost.
I don't know, you kind of just pick up on the syntax of the first person you learn from, and that's what you like.
My problem is I've been learning from him, and I look at the way you do. I'm like, that's way better.
Okay, hopefully we don't need the CP here, can't indent much. So we're right here. If Brown failed to deliver the goods, D for delivery, okay. If Brown failed to deliver the goods on the due date, Brown did not perform the contract. So, not D, not contract, implies not contract, am I reading that right?
This is a mistake. Or thinking it through. It's just because he failed to deliver does not mean it's not D. It's just D.
Why?
D is failed to deliver.
This is a big question I have, is how do you determine when, based off of the language? it's
It won't
not-
matter as long as we interpret it consistently.
That's what I found.
So I'm going to use D for he did deliver, and we're going to put not D in there, and it's not going to matter.
It won't
It's
matter.
just complicated.
It will not matter.
Because he says he fails to deliver in every statement that D is applied.
Oh, okay.
Yeah,
So it's
so we were
consistent.
able to, yeah, if it's consistent.
So as long as you're consistent, it doesn't matter. So if Brown failed to deliver the goods on the due date, Brown did not perform the contract. The fact is that Brown did not enter into the contract and failed to deliver the goods. So not contract and not delivered, right?
Right.
Yeah.
Therefore, Smith will win the lawsuit. So we're
Wait.
trying to prove W.
Yeah.
So we only had 3 premises. They were just somewhat convoluted. Okay. I do not see off the top of my head whether this follows or not. So we're gonna have to play with it.
You gotta use
Three
conditional
is
proofs.
not delivered, it's, performed.
Thank you. Wait, there isn't a perform.
There is a perform.
Oh, there
He
is a
didn't-
perform.
Yeah,
Okay.
he did not perform the contract.
The fact is that Brown did not enter into the contract,
And,
so that was not C, and failed to deliver the goods.
So D.
So D.
do you miss the?
I think you read the line above it or
Line
something.
above it, line above it says did not perform the contract.
So I messed up this one, is what you're saying.
It's P.
Instead of C,
If Brown
Yes.
failed to deliver the goods on the due date,
cause he.
failed to deliver, Brown did not perform. Okay,
Okay, yeah. I
Yeah,
found
that one's
one.
not-
that is what you were saying.
Yep.
Okay,
It's
that
wrong,
is
so-
glad that we got that. That would have been a nightmare. Okay,
So
then
this
we,
is a common, kind of conflict in my reasoning. One thing we can derive is not C and not D. And because all of our, premises can be concatenated, I guess, I have a better word, with, and statements. Could it possibly be easier to just put those on their own separate lines? Not C and not, so it's,
sure,
yeah.
sure. We could quickly go like this if we wanted. Let's say not D. This is tautologically implied by line 3, and it is only dependent upon 3 for its validity.
But you could, I mean, I'm wondering just as like a shortcut, because logically it's the same thing, that you just, for premise 3, you just say not C. And then for premise 4, you say not D.
No, here's your premise. I wouldn't mess with that. I would just split it up like this if you want to split it up.
But that's implying that a sentence, is what defines the boundaries of what a premise is.
Well, it is. We're listing out the sentences we were given.
Okay, that's cleared it up for me. I was curious about that.
Okay, so this is perfectly fine to break it up like
How
that.
can you say not D? How can you say that not D is true? How can you just say not D?
This is saying C's false and D's false. So I know D's false. I know that from here. And I know C's false. I know that from here.
If a single one of them is false.
No,
that's
it's saying
false.
C is false and D is false is true.
Right. If I tell you I'm not a billionaire and I don't own a jet, you know I don't own a jet and you know I'm not a billionaire.
Okay, because we have
So,
Because that's one thing that really helped me trying to connect all this is the understanding that all premises are conjoined by the and statement, the and condition, or the and symbol.
wherever makes it quick. Okay, so we split those up. What can we conclude now on line 6? From either of these,
Not P.
we can conclude not P. That's combining 2 and 4 together. So we know not P. This is tautologically implied by lines 2 and 4. This is now dependent upon 2 and 3 for its validity, those two premises. Right?
Yeah.
Okay, now we know not P.
So we know C.
We know that not C is true, so C is false. Or, okay, so true or false is true. So the premise 1 is true implies not, not a win, and we're trying to, so our whole statement's false. This whole thing's false.
So because we know not P, when we know either not C or P, and P is false, then we know not C. Right?
Oh wait, hold on. I think I remember a trick we made an assumption. It was like a conditional.
I missed what you were saying. You're saying what?
I'm just talking about.
Because of not
Because
she's
we
saying we know
know-
C.
Because of not P, we know C. How do we know C? We can't know C because we know not C.
Line 1.
So there's a contradiction here.
You're trying to figure
There's
out.
a contradiction. You're right.
There's a contradiction
Yeah,
because we know
line-
not C or P, but we just found out.
We do not know, we don't know not C or P. We know if we have not C or P,
Oh,
then we have
Yeah, because it's something.
not.
not W.
So
But we don't have not C or not P. We have not C and not P.
Well, hopefully we can't have not C or P.
So that it's false. Right?
So, not, okay. So, trying to think about the best way to say this, but yes, you're seeing that this right here is false.
Yeah.
Well, yeah.
But
no,
then,
it's true.
we're able to conclude that.
Hold on, no.
So this one, this is one where the conclusion is not going to follow.
Right.
So we're going to have to come up with some interpretation. So we need to come up with an interpretation where this is true, this is true, this is true, and this is false.
We just did.
Well, now we need to come up with our actual interpretation. So we want W to be some true statement. We don't care what the statement is, but W to be something that's true. We need, if W is true, not W is going to be false. When is an implication false? When the antecedent is true, but the conclusion is false.
Right.
So we need this to be true.
Which is not the case.
So this will be true if C is equal to false. That will make this for sure true.
Mm-hmm.
P can still be whatever we want. We're not restricted on what P is yet.
Well, one strategy I used is that technically I can,
And then D also has to be false.
I can apply the statements that already exist. 4, 5, and 6 already can say, well, D's not true.
True implies, so I need P here.
P
I
to be
need not
false.
P to be true, so P has to be false.
But that's big. You can actually assume that off of 4, 5, and 6.
Well, so forget 4, 5, and 6 now. Go back to our premises. We're saying that the conclusion does not fall from our premises. In other words, we are saying it's possible for all our premises to be true and our conclusion to be false.
Right.
And that's the scenario.
Oops. Why did I pick W to be true? I want W to be false.
Yeah. Because you want the conclusion to be true.
So if W is false,
Then not false is true.
then not false is true. Okay. So let's make sure that this works. Let's evaluate this. True or false is
True.
true. True implies true is true. So this interpretation made this one true. Okay, we're good there. Let's look at this one. True implies true is true. Now let's look at this one. True and true is
True.
true. So all our premises were true and our conclusion was false.
Okay.
So conclusion does not follow. There's no way to prove it.
Yeah.
All right. We want to try and find another proof, or you want to move on? Want to move on? Okay. Consistency of premises and indirect proof now. Okay, so this was the section we were on. We never did example 4. Let's do example 4, even though it's very similar to what we just did. It's one where we're supposed to show the premises aren't valid. So let's do this one really quick. So looking at example 4, if the contract is valid, then Horatio is liable. So valid implies liable. If Horatio is liable, he will go bankrupt. So 2, liable implies bankrupt. As a matter of fact, the contract is valid and the bank will loan him the money.
You missed one. If the bank will loan him money.
Oh, thank you. Just read it to me.
If the
Oh,
bank-
crap. I can't use loan because I use L. I'll use M for money. Money from bank. M. Okay, read it.
If the bank will loan him money, he will not go bankrupt.
They're not bankrupt. Okay, and then what was the last one?
As a matter of fact, the contract is valid and the bank will loan him money.
So valid and money. So our job was to show that these premises are inconsistent, I think is what he's supposed to do. The purpose of the following example is to illustrate how the rules of logical inference may be used to show us that premises is inconsistent. So I think here he's going to derive a contradiction to show they're inconsistent. Yeah, he's going to give B and not B. So let's try that. Derive a contradiction to show that these are not possible. So premise, 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 premise. Rather than coming up with the interpretation, this time we're going to show that our premises entail a contradiction.
Is
So-
where one, doesn't that mean where one is true and for one to be true, the other one has to be false?
We're going to get B and not B, or M and not M, or B and not B. We should be able to get any of them, basically. So we probably won't get the same thing that the author got. Okay, but let's start working with it. So I know V and M. Maybe I'll quickly say, therefore we know M. This is tautologically entailed by 4, and only depends upon 4. Okay, so now we know M. What do we know?
Not.
We know not B, combining these two together. So for 6, we can say not B. This is tautologically implied by 3 and 5. Am I looking at that right? dependent upon premises 3 and 4. Good? Okay. Line 7 now. What are we going to conclude? If we could just take the V from here. We haven't used the V information yet, so we'll just take that. This is tautologically implied by line 4, and it's only dependent upon 4. Okay, now focusing on the V, what can we conclude?
No.
L.
Yeah.
So then we can get L. This is tautologically implied by lines 1 and 7, and now it's dependent on premises 1 and 4. Okay, now what can we conclude?
B.
B. That's from line 2, so we get B. This is tautologically implied by lines 8 and 2. 2 and 8, keep my order correct here. And now we are dependent upon premises 1, 2, and 4, right? Okay, and now what?
B and not B.
Drum roll, B and not B. This is tautologically implied by which lines?
6 and 9.
6 and 9. And now we are dependent upon premises 1, 2, 3, and 4. So premises, all the 4 premises together until a contradiction, and so something's got to give. Our premises are inconsistent.
Yeah.
We could have also come up with the interpretation. Oh, this wasn't an argument seeing some conclusion followed. So this is different from the ones we were doing before.
Yeah.
The other ones we were given a bad argument where supposedly some conclusion followed from some premises. This time we were just given a set of premises and we're showing those premises aren't even consistent. No point even trying to reason about it. We'll get a contradiction if we do. Good?
So that's how we know, basically, we come to some premises that contradict each other, obviously, because not B and B is definitely not true.
Yeah. You can't have B and not B, so our premises must be inconsistent. Okay. And then example 5. That was redoing older example with a reductio ad absurdum proof. Here's example 5. So, guessing we'll have at least 4 premises. Okay, one of you want to just read it to me so I don't have to keep bouncing?
If 25 divisions are enough,
Divisions are enough.
then the general will win the battle.
Okay,
Either 3 wings of tactical air support will be provided,
air support
or the general will not win the battle.
or not win.
Also, it is not the case that 25 divisions are enough, and that 3 wings of tactical air support will be provided.
Is that a not on the conjunction or a not A and not B?
There's no comma, so my assumption is that you would wrap
It is not the case that 25 divisions are enough.
And
Yeah, it's going to
I
be
would parenthesis that.
not
Second.
A, not D and A. D came first, right?
yeah.
It is not the case that this and this. Okay, next.
Therefore, 25 divisions are not enough.
Okay, so we're proving D. Let's just to double check, make sure I didn't make a mistake there. Let's look at the author's encoding, and it should be very similar. Not D and A. Okay, so. Oh, we're trying to conclude not D.
Oh, yeah.
25 divisions is not enough. D was
Yeah.
25 divisions is enough.
Those are so sneaky.
Yeah. you
Yeah,
really have
gotta make sure you read it
double
right.
check.
Okay, so now, he wanted us to do this proof with reductio ad absurdum, proof by contradiction. So I'm going to assume D as a premise, show that leads to a contradiction, and therefore D is inconsistent with these premises. So it has to be not D.
So you're saying it.
Or in other words, we're using this rule. If P, our premises, and not D imply contradiction, then our premises imply D. Another way to say it.
That's really handy.
It is really handy. Okay, so for here, we're going to introduce D. Indent it because I promise later we're going to get rid of it. Wait, Oh yeah, D, because the conclusion we want is not the negation of what we want.
Yep.
And with this, we better get a contradiction. Okay. Maybe rewriting line 3 here, just to, so that we can see it. This is the same thing as not D or not A. This is tautologically equivalent. Scoot that T over a little bit.
Why didn't you indent that as well?
This is where I'm starting my proof by contradiction.
And then you unindent.
And then I unindent when I get rid of the premise I was trying to get rid of.
Interesting.
But 5 doesn't depend on 4.
No, it doesn't. So it is only dependent, so this is tautologically implied by 3. And it is only dependent upon 3 for its validity. Okay. So now, what can we conclude?
Well, we can first do 1, that's easy.
So really quick, we do 1, and what does that give us?
W.
W. So this is tautologically implied by 1 and 4. And we're using premises 1 and 4, right? Okay, so now we have W. Now what can we conclude?
Not A.
We can conclude what?
Well, so if, oh wait, that's not implied, never mind. I don't know. Let's see.
You need to write 7, not W, right there.
Oh, A has to be true, doesn't it?
A has to be true. Good. Because these, oh sorry, no, A has to be false.
No, well, okay, that's where a contradiction.
D has to be false or A has to be false. But D is true.
Premise 2 says A has to be true.
Or W false.
Well, okay.
Yeah, I see what you're saying.
Okay,
You're seeing ahead, just doing it one step at a time.
Sorry.
Nope, you're fine. We just looked at different ones. So, not A was tautologically implied by these two, right? So this was from 4 and 5. And so this is dependent upon premises 3 and 4. Right?
Yeah, that's right.
Okay, now, why did I put
Yeah.
numbers there? Okay, 8. Okay, now, go through your thinking.
Okay, so if W is true, that would make A or false. Therefore, A has to be true for that premise 2 to be true.
So we know that W is false or A is true. Is W false?
Yes.
No,
Well-
W is true.
Or, yeah. But
So we know W is false or A is true. Is W false? No, so A must be true. So we're able to conclude A here. This is tautologically implied by 2 and 6, right? 2 and 6. What are our premises? Premises from 2 is 2. Sorry, slanted that horrifically. 2, and then 6 we had 1 and 4. So 1, 2, and 4. Those are premises for those. And then finally, what is it?
A and 9.
A and 9, our contradiction. This is tautologically implied by line 7 and 8. This is dependent upon for its validity 1, 2, 3, and 4. So we got a contradiction from all those premises. Something's got to give. And so, 10, we are able to conclude then the negation of what we started with. So we're able to conclude then, not D. This is by rule R, A, as of my own practice, I say where our proof by contradiction begin and ended, 4 through 9. And so now we are no longer dependent upon 4 as a premise. We are instead just dependent on 1, 2, and 3. We're just dependent upon fancy P. Fancy P was a conjunction of these ones. And this was our not S. So fancy P and not S led to a contradiction, therefore our premises alone entail S. Follow the thinking there? Okay, and that gets us caught up with everything. That's the end of that section. Unfortunately, we didn't get to grammars today.
Hey, you was a lot.
Yep, doesn't matter. There's no timetable, there's no rush. Rather make sure we feel comfortable with the stuff than just push forward. So don't necessarily want to just do anything we have on the board.
I'm still not intuitively comfortable with why we can introduce some random thing, prove something, and then erase it.
And then get rid of it.
I understand the rule, I just don't, it just doesn't intuitively make any sense to me.
So, if my premises and S being true are for sure impossible. So our premises we're already taking for granted. These ones are for sure true.
You're talking about the original three premises.
Yes.
Okay.
So we're always taking our premises for granted. So if my premises and S are for sure false, so if this is for sure not the case, then what do I know? I know my premises are true. I know my premises and S together are for sure false. Then I know it must be not S.
Right.
You could just,
That's the same thinking.
you could just plug this tautology in.
Yes, but
Oh, 'cause
she
they're-
wasn't seeing it from that, so I was trying to come up with another way.
They're just and.
Yeah, this P is just stands for this and this and this and this. So, right now, just to be a little bit pedantic one time. So, D implies W, and A or not W, and not D and A. That is what our fancy P stands for.
Yes.
So we showed that this all together and D implied something that was for sure false. So all these together, maybe put one more big bracket around it to remind us of what our P is. Here's our fancy P. So fancy P and D was impossible, led to something impossible. Therefore, it had to be fancy P and not D. Little bit different from that. If fancy P being true and D being true led to something impossible, then if fancy P is true, that means D must be false.
Okay.
Because if fancy P is true and D is true, that's impossible.
That makes sense.
Therefore, if fancy P is true, D must be false.
Gotcha. That makes more sense.
And that's the logic trying to be expressed in that truth table. Good?
It's so helpful for me when you can connect stuff like this back to the roots of fundamentally of what's happening behind the scenes, basically. Where it's obviously very elaborate and what's the word? But it's the same concept, but it applies to rules that we already understand.
Whatever makes it quick. Just being exposed to it, you never know the theme that's going to make it click. So you just keep going over it again and again. Okay, any other questions? Anything else you guys want to talk about? All right, well, there's a big old day of just a bunch of examples, and then we'll continue with new material next week. And we'll find more careful ways to break down these sentences rather than making the stupid mistakes we make because we're representing it with one letter.